Thank you very much. Yeah, it's a pleasure to be here back again. And I want to talk a bit about like the work that I've been doing this past year. And well, it's on symmetric quantum computation, and it's based on joint work with Tom Gur and Sergei Structure. And then to get right at it, like the theme. Okay, so first, like a general outline of the work that we are trying to do. So the theme is to search for general principles that indicate the possibility for quantum advantage. So I actually see this as like the main problem of quantum computing, of like quantum complexity theory, more specifically, which is not just to find problems that are hard for classical and easy for quantum, but like to find the principles that explain why those problems are better, like are more amenable to quantum methods and classical ones. And this is a very broad theme. So we have a goal within this team, which is to investigate the relationship between the symmetries of a computational problem and possible quantum speedups. And then we have the method of how we want to achieve that goal, which is like we develop a new framework of symmetry restricted computation. So it's essentially a kind of restricted model of computation, of quantum computation, where the symmetry, or where the restriction is symmetry based and depends on the problems, not like universal for all problems. And in this talk, what I really want to do is mostly to motivate and explain the framework. And like, this is the main goal of the talk. Afterwards, I will also give some results, but like those are kind of a secondary importance in my view. And so like, whenever you have questions, please ask. I want this talk, especially the first part, the motivation and introduction model, that's should be understandable to everyone. And another thing that I want with this talk is that, well, we are kind of trying to open up a new line of investigation. And so there are several open problems that I consider very interesting. So this is also a kind of an invitation to join in on the fun. Yes, to get to it. So why symmetry? So the thing that you have to know is that like a lot of very important computational problems, they have rich groups of symmetry under which they are invariant. So for instance, in machine learning, everybody knows this, like machine learning, the ultimate goal is to distinguish cat pictures from dog pictures. And everything else is secondary. And like, you know that for this problem, it should be kind of translation invariance and rotation invariance of the pixels. Like if you translate a cat, it will be a cat. If you translate a dog, it will be a dog, and this kind of things. So these problems, they have this symmetries embedded into them. And so, well, this one example. Another example, like not quite as important as cats and dogs, but still important, like combinatorial optimization, essentially, and then like more more restricted, like the graph problems in combinatorial optimization, which can model a lot of different things, but the underlying structure, which is the graph, is like just an abstract structure which has a lot of symmetries, and then like the way that you choose to label the graph shouldn't matter. So the problem is invariance on the graph isomorphism, or actually under any permutation of labels of the vertices in some sense. And also, like more generally in physics, symmetries are really ubiquitous and they are really important, and they dictate the physical evolution of the system and everything. So like whenever you have like a problem coming from physics, it will very likely have a symmetry that comes from these physical considerations. And so that's also another kind of important place where we can get symmetric problems. And something that has been realized several times is that it's very important to leverage the symmetries of the problems when searching for solutions for them in order to make it more efficient. And I like very much this this phrase here from this book, Geometric Deep Learning by Bronson et al. They say that exploiting the non-symmetries of a large system is a powerful and classical remedy against the curse of dimensionality. And this remedy has been like applied to all these three examples and like to many other examples. And like the main idea is that by if you have a lot of symmetries, and then the solution to the problem will usually like you can make it precise, but it will be symmetry invariance, like invariance under the symmetries. And then, but the search space that you have to search for the symmetric solutions is much smaller, and you'll have a lot of a lot of tools from like representation theory, for instance, to help with that. So it's very important to consider the symmetries when designing efficient algorithms to solve a problem. And yes, just to say things that this geometric deep learning is, oh yes, please.
Sorry, can I ask a more conceptual question?
Yes.
So, at least in physics, there's a lot of problems, but they're made only easier by a constant if you make them, like if you exploit this symmetry.
Yes.
Right? So, why do you expect symmetries to give you a significant or at least polynomial advantage?
Oh, that depends very much on the specific problem. I mean, they make the problem easier. It doesn't mean that they make them easy. Sometimes it will give, like if you have enough symmetries, then you might be able to construct efficient algorithms for them just using those symmetries and representation theory. Sometimes it might not be possible, but at least you won't have to search the full, like 2 to the n dimensional space, Hilbert space, for the solution if you're dealing with n qubits.
Sure.
You can like restrict the solution, might be still exponential, but it will be a small exponential. Sometimes it's the best you can do, but sometimes it isn't.
Okay, cool. Thank you.
And yeah, so this geometric deep learning is kind of a subfield of machine learning where they really use the symmetries as constraints in the computation to make the model perform better. So this is very much in line with what I am trying to do here. But I mean, I'm doing something more, more general than trying to learn cat pictures and dog pictures. But it's pretty much the same idea. Okay, and then like with this, we see that an abundance of symmetries is it emerges as a general property of computational problems that indicates whether there is a possibility for efficient algorithms, either classical or quantum. As I said, this is mostly because like you have more tools, and then you also have like a much smaller search space. And as I said, I see as the main problem of computational complexity theory in general as to finding these general principles that will indicate the possibility of efficient algorithms. So how can you decide if a problem is hard or easy? And the main question that I want to, well, that I am working on in this line of work is to ask like which types of symmetries allow for large quantum speedups. So if symmetries are good both for classical algorithms and for quantum algorithms, it's actually a very subtle question whether they contribute to quantum speedups or they are against it, because it's about the relative power of those. Oh yeah, and then some questions similar to this have already been asked. So like, for instance, like how much structure is needed for huge quantum speedups? This is the title of a talk of Scott Aronson. And then he has like this beautiful illustration here. I think this is a bit, to be honest, a bit naive. It shouldn't be just like on the top, if we have a lot of symmetries, we have a big quantum speedup. It's actually a lot of structure. It depends on the type of structure. Some structures are amenable to quantum speedup, some are not. But this is a good cartoon in the sense that you need a lot of structure to have a lot of speedup. And also, the structure I see as something dual to symmetry. In the symmetry side, we have this paper of Schwartz et al. That is called Efficient Classical Algorithms for Simulating Symmetric Quantum Systems. And then they observe that like if the symmetry group of the problem is very small, so let's say it's a cyclic group, so it's, yeah, it doesn't do much, essentially. And then you kind of have no hope of using this to improve your quantum algorithms, like to get an exponential speedup. And if your symmetry is very restricted, so if it's a full permutation symmetry, then this is essentially what they show here, is that you can efficiently simulate the dynamics of a symmetry invariant Hamiltonian in polynomial time on a classical computer. So if the symmetry is also too restricted, there is no quantum advantage or only polynomial quantum advantage. And then it's kind of in the middle here, but it's not just like being, I don't think it's just the size of the group, it's what specific group itself will be amenable or not. And the proposal that we have for studying this problem, for making progress on this question, is to embed the symmetries in the computation. Instead of just considering algorithms for symmetric problems, so we consider symmetric algorithms, where the symmetries are kind of come from the problem and go into the computation. Let's see. Yeah, so we come to the main model. So symmetric circuits, they are essentially those quantum circuits for us that respect the symmetries of the problem in consideration. A bit more precisely, I will be more precise later, but for now, what I want you to take is that every symmetry of the inputs can be extended to an automorphism of the circuits. So it wouldn't change the circuits by applying the symmetry. And to understand better, I have a couple of examples. So the first is this permutation invariance learning problems. So there's also this field of quantum machine learning, and then they do like this. There's this paper by Shatsky called Theoretical Guarantees for Permutation Equivariant Quantum Neural Networks. So they propose quantum neural networks that have these symmetries, this permutation symmetry, embedded into the circuits. And they show that if you do this, like if you restrict the computation to respect the symmetries of the problem in this case of like full permutation symmetry, then you have all the good stuff essentially. So like you have efficient overparameterization, you have like absence of barren plateaus, you have like good generalization. And so like getting the symmetries from the problem into the circuit itself that's going to try to solve the problem through these quantum neural networks is a very good, very important thing to have, or that's what they show.
So don't you also get like efficient classical simulability?
Yes, that was a paper.
That's sort of the problem.
Exactly. That was a paper. After this, it was actually a paper like kind of referencing this as the main reason why they were doing. But this is a bit more complicated because like, okay, if both the inputs and the output are classical, then yes, you'll get a polynomial time algorithm, classical polynomial time algorithm for simulating it. If they are actually quantum, then I mean, you have to think, and like there is also still a polynomial separation, but yes, this permutation symmetry morally does not give an exponential speed. Another example, which I think is more instructive, and it's also a simpler example, is like state discrimination. But by this, I mean the very simplest possible model of state discrimination. You are given two single qubit states, psi and phi, and then you are promised that either they are the same, psi is equal to phi, or that they are like kind of far from each other, they are not too close. So their inner products at most 1 minus delta for some constant delta. And then what you want to do is to decide which of these cases holds. And here there is a symmetry involved, a very simple symmetry, because this problem, both the promise and the outputs, they are invariant under this changing of psi and phi. Like if you call psi, the state was previously called phi, and the other way around, it doesn't change anything. And so the symmetry group is essentially S2, the symmetry group on two elements.
There's also unitary symmetry.
Yes, there are more symmetries, but here, oh yeah, something that I might have said before. In this talk, I am considering just discrete symmetries. Yeah, it's a more kind of computational complexity approach to symmetry than a physical one. But yes. Okay, does anyone have any idea of how to solve this problem? Is there a simple algorithm to do this? Yeah, exactly. The swap test. That's a very good algorithm, like very simple. It's just illustrated here. So you have here the phi and the psi, and then you have an extra qubit. Then you do this and measure. And then the probability that the output of this measurement is 1 will be given by this. So it's actually 0 if psi is equal to phi. And it's strictly greater than 0 if psi is not equal to phi. And it's like bounded away from 0 under this promise. So you have like a bounded error test for this problem. And then you see here that's like, since the swap gate is symmetric with respect to its two inputs, then this can be seen as a kind of symmetric quantum algorithm in this sense. But I don't feel very, I don't believe this is a real symmetric quantum algorithm because this kind of controlled swap, is it really like a gate from the gate set? Is it really an elementary gate? It's not usually considered. So let's suppose that instead our gate set contains single qubit gates and CNOTs and TOEFLs. Those are our universal gate set. And then what can we do? The thing is that it's possible to represent a swap as 3 CNOTs. And then there's a very easy way of doing this. And if we do this, then you obtain this circuit here. That's now it has kind of elementary gates if you consider TOEFL as an elementary gate. And it does exactly the same as before, right? So is this a completely equivalent circuit? Am I correct? And the answer that I'm looking for is no. The answer that I'm looking for is that this is a very bad circuit. I don't like it because it's not symmetric. Look, there's only one head of a Toffoli gates on phi, and there are two heads on psi. So we can distinguish both them, one from each other, by these circuits. Even though it was equivalent to this, like as an operation, it's not symmetrically equivalent. So I don't like these circuits. What can we do? It turns out that like if we allow for additional ancillas, then we can make it symmetric again. This is a circuit that is equivalent. Now it has an extra qubit, but it's an ancilla that starts at 0 and ends at 0. So we usually ignore those. And you'll see that it's completely symmetric under permutation in the sense that if you permute phi and psi, then what you are doing is just permuting these Toffoli gates within these layers. But these layers, these Toffoli gates that you are permuting, they are commutative. They commute with each other. So there's no intrinsic order. It's just like a feature of the representation. It's like completely arbitrary feature, which one comes first and which one comes after. So if you change those two, you are going to change the order in each one, but the circuit is the same because they're commutative. And now this already has all the ingredients essentially for my notion of symmetric quantum computation. That's like you have these inputs here. Well, there's qubits that represent the inputs, and then there's a symmetry group acting on them. Here, the S2. And then if you permute those, then it becomes it is an automorphism of the circuit in the sense that it doesn't change the circuit at all, up to like these commuting transformations. So that's pretty much like the intuitive idea of what it is. So again, symmetric circuits are those that respect the symmetries of the problem considered. And a way that I like to think of it is as a kind of minimal computational model where we, yes.
So can I ask a question? Like, can you go back one slide? So you require the symmetry only on the data qubits on these.
Yeah, exactly.
Like, can you cheat by just like kind of moving the data somewhere else and then have the symmetry, or like this moving process itself?
This moving process, yes. As soon as you interact with the qubits, I call active qubits. They are the ones that represent the inputs. As soon as you interact with them on an ancilla, then the ancilla kind of gets entangled. Like entangled, not in the quantum sense, but like in the symmetry sense. Whatever you do on the ancillas, that's if you just copy those to, I mean, you can't, but if it was classical things, then you could copy those to two ancillas, and then you say, okay, we don't have symmetries there. But then as soon as you do a synods from this to one ancilla and from the other to the other ancilla, then the symmetry there kind of has to respect the same symmetries of the active qubits. So yes, you cannot cheat just by doing this. Okay, and then I see this as a kind of minimal computational model. If you consider asymmetry as a computational resource in algorithms, then what we are considering is this computational model where you do not have this extra computational power given by asymmetry. And there's no extraneous breaking of symmetries or of abstraction. So if you think of an algorithm abstractly, like on the level of graphs, for instance, and then you don't want to differentiate graphs that cannot be differentiated like by degree or by the number of triangles it belongs to or something. And then, yeah, what I'm trying to say is that the usual algorithms that you have at a high level, they can usually, like if you try to convert them to a quantum algorithm or a classical algorithm, they will be symmetric when you convert them in the sense that I defined. And this symmetric computation is well studied in the classical setting. They are called usually symmetric threshold circuits, and they have a deep connection to logic. So they are equivalent to something called fixed point logic with counting, which emerged as a logic of reference on the quest for trying to find a logic that captures exactly the polynomial time computable properties. It doesn't, but still it's the logic of reference is kind of the best they have in some sense. Or, well, now they have a bit better, but still that one is one of the most natural ones. And then it's remarkably powerful. So even though you restrict the computation to preserve the symmetries, you might wonder, oh, maybe I can't do anything interesting. But then it's shown that it can do a lot of interesting stuff. So like even solving LPs and SPPs in a way that respects the symmetries of like this matrix symmetry, because LPs and SPPs are given in terms of matrices. So the symmetry is given by column and row permutations. And you can do a symmetric circuit that solves STPs and LPs in a way that respects those symmetries. You can also find like maximum matching. Oh, yeah, I didn't read that, but that's true. And also like decide all minor closed properties of R. So like there are several interesting properties that can be decided in polynomial time by symmetric classical circuits and quantum as well. Yes.
So here, when you talk about symmetry of graphs, you only think of symmetry of the nodes.
Yes, exactly. It's
You don't go looking deeper inside.
No.
Graphs.
It's
Their symmetry is also exploited in a very powerful way.
Yeah, no, what I mean is just the symmetry of the abstract structure, which would be like
Permuting the nodes.
exactly permuting the nodes. Exactly. And exponent, yeah, even though it's a very powerful model in some sense, because it can do some very impressive stuff, we can prove exponential lower bounds for circuits, for symmetric circuits. And this is something very interesting. So we can prove exponential lower bounds for the size of Hamiltonian cycles, which is NP complete. So like we expect it to be to require exponential size circuits, symmetric or not, but we cannot prove non-symmetrically, of course. We can prove symmetrically at least. Then for computing the permanence of a matrix also, and for other problems like XOR I will come back to that later.
Sorry, Davi, can I
Yes.
ask like still about the previous slide with your example?
Yes.
With this control swap, like, I mean, you require basically some extra workspace and a bit more time to implement this. Like,
Yeah.
Is this a problem, or like let's say you have some algorithm which you know can be converted to respect to symmetry, but like, can this conversion kind of make it inefficient?
Yes. There are examples in the classical setting. There are examples where there's an efficient algorithm, but there's an exponential lower bounds. Well, the example was given here, XOR. XOR can be solved by, well, I will get to that later, but like it can be solved non-symmetrically, but it cannot be solved symmetrically without exponential slowdown. Okay, and then in the quantum setting, I argue that like this computational model elucidates the role of symmetries, the relationship between symmetries of problems and quantum speedups. And there is a potential both for strong lower bounds, because we have those in the classical setting, and also for quantum advantage, because we have this strong lower bounds in the classical setting. And then if you can find an algorithm, efficient algorithm for one of those problems, then you get quantum advantage. And now going slightly more abstractly, what we are doing here is considering a kind of restricted model of computation, where the restriction is symmetry based. So it kind of makes sense for you to compare with other existing restricted models. So the most famous one, perhaps the most interesting one, is the query model. So, so there are advantages and disadvantages that I want to talk about. So the first advantage is that it allows you to focus on kind of limited resources. If like what you are doing the query is something that is very expensive, and then you really will want to make fewer queries to that, and then it allows you to model that thing. It also allows you to model learning from a process that you don't know the inner workings of, or you don't trust them and you want to test it. Then this is also another thing that it allows you to do very well. And also something that's got hammered in Ronald's lecture notes is that like most of the quantum algorithms, they are very query model friendly. So like Shor's algorithm and like Rover and amplitude amplification, all the good stuff, they kind of are given in a query model friendly way. And so I think this is a very good advantage. But there are some disadvantages, of course. One interesting one is that it's not always natural. It's not always reasonable even, I would say, especially if you consider only query complexity. What I mean by this is essentially like this quest of trying to find the maximum query complex separation. And then there was like Scott Aronson and Andres Ambainis, they were saying, okay, you have this like 1 versus n query advantage separation. Can you do better? Like what's about 1 versus 2 to the n? And then I don't really understand because like there's no function that maps 1 to n. There's no function that maps 1 to 2 to the n. Those are completely unbounded. It's kind of, and this really bothered me until like you pointed out that the reason is that this is not supposed to be a reasonable model of computation. Like, yeah, sometimes it's just not a reasonable model. Sometimes it is, but that's okay. And also related to this, it's hard to interpret the results in the usual circuit model. So say I have an exponential lower bounds in the quantum query model, and then I want to instantiate this query with an algorithm, like some algorithm that I know. And now, do you still have this exponential lower bounds? Or can you use the structure of the algorithm that you instantiated the query with to get like a polynomial time algorithm for that? And this model, it doesn't say anything about this. That's why it's a restricted model. And then another model that's interesting is like shallow circuits. Let's say bounded depth quantum circuits. This has been very well studied in the last few years, and it has a very good motivation. So for instance, there are the current technological limitations of quantum circuits. So the depth of the circuit is related to the time of the computation. So the decoherence time of the qubits will impose a hard limit on the depth of the circuit that you want to compute. And there's also, well, it can also model like maximum time allotted for computation. So if you're a company that you are doing computations for a client, and then suddenly you have twice the number of clients, they are not going to be happy if you take twice as long to give the answers. So kind of you have, if you model this time by parallel computation time, so like depth, then this would also model this thing. And they are mathematically very natural. So I think the good thing about this shallow circuits is that they have a very good motivation. But there are bad things. One bad thing is that they are too strict. So like why just bounded, not like maybe polylogarithmic or something. And it's not always meaningful in the sense that, well, everything that we will ever do has bounded depth. That's like the sense of the universe. Then you say, okay, of course, this is an abstraction that we do, and then it works on some ways. And then I say, yes, but then if you take a look at the quantum advantage that we get usually, they are not meaningful in this sense, because like they will kind of only be relevant in astronomical scales that we'll never use. And I mean, those are still interesting mathematical results, but they go against the good motivation. So in this sense, it's a disadvantage. Another one is that we can go significantly further classically. So in this abstraction, we can go up to like polynomial depth in the classical setting, like very efficiently if the polynomial is small. And quantum in the future. And like, so it has a good motivation right now. Maybe in 20 years, it will no longer be a good motivation. So that's another one. And now finally, to compare with our model. So symmetric circuits, I would say they have a good motivation to like study the role of symmetries in quantum computation, quantum speedups. And also something a bit more secondary, but still interesting, is that they naturally extend an interesting classical model that has been well studied in the classical setting. And also many algorithms, they are naturally symmetric. Algorithms that are given at a higher level of abstraction, they will naturally be symmetric. Well, usually, not always, but usually, yes. You can make it precise in the language of logic, but I'm not going to do it now. And of course, it has disadvantages. What are those? Well, it's hard to interpret the results in the unrestricted setting, like in the query model. Okay, say I prove an exponential lower bound in the quantum symmetric setting. Does it still hold if I don't require the symmetry? I mean, this model doesn't say anything about that. So you'll have to think like, is there a reason to expect that breaking the symmetries will significantly better the algorithm or not, like allow for others or not? This is something that's like outside the scope of this thing. It should be, it's another input. And yeah, related to this, like breaking symmetries is sometimes essential for symmetry. But I would argue still that here, it's very interesting to prove that they are essential for symmetry. Like, when do you need to break symmetries in order to have efficient algorithms? I find this like a very interesting, like less importance maybe, but it's still a very interesting question. So how do they compare? I would say that these models don't really compare. Each one of them illuminates a different aspects of quantum computation. And like they focus on different things. So actually, if you try the same problem on different models, then the insights that you glean from one will be completely lost on the other, because they are trying to focus on different things. And so they are fundamentally incomparable. However, as long as we, like the limitations of quantum computation in the unrestricted setting are beyond us, which can be a very long time, I would say that it's just through a combination of all these restricted models that you can get a more complete picture. So I would actually think that it would be good if more people came up with more restricted models, as long as they are natural and interesting. And then we'll get a much better picture of like unrestricted computation just by combining those. So that's my pitch. Okay, that's what I wanted the most to talk about, but now there are some results as well. But I hope that everyone understood the first part. Are there any questions for now? Okay. Oh, yes.
I can ask one question, maybe. So I know, like in classical complexity theory, there was a long line of work about this dichotomy conjecture about saying, you know, whether or not the CSP is solvable in polynomial time, and there was also all about symmetries. I was wondering if there's any connection between what they did there and what you're trying to do here, or is
there is a connection in spirit, but
Yeah.
not formally.
not formally? Yeah.
Because their symmetries are kind of like higher order symmetries. They are like much more strict or like different, essentially.
I see. I see.
But yeah, it's kind of morally similar, but not formally similar. Okay, so now the definitions and results. Okay, so first of all, what's the gate set that we allow? So we allow all single qubit gates, like this is something quite common, plus the threshold gates. The threshold gates is like you have a bunch of qubits here, and then a target qubit. And then it does nothing to these qubits, it just computes like whether their Hamming weight is larger than a certain threshold. And then if it is, then it's like flips the target qubit. So for instance, like the quantum AND gate, the usual way that you define it is like this, but like here the threshold is n, is the number of qubits. So it only gets flips if every qubit in the support is 1. And also the quantum OR gate, where the threshold would be 1. So if there's at least 1 qubits in this computational basis that is 1, then it will flip the target qubit.
So you're allowed to apply this gate only on a whole, but not like on.
No, we are allowed to apply on any subset, yes. But then this subset, like you have to do it symmetrically. So if you apply once, you have to apply several times in all the all the symmetries, essentially. But yes, it's arbitrary. Okay, and to talk about the symmetries, we have to define this automorphism of quantum circuits. So those are essentially, as I said before, they are permutations of the qubit wires, which preserve all gates up to commuting reordering. So for instance, if we permute like this first and second gates, first and second qubit wires, then this gate here would actually become like this, I think. Yeah, no, if you permute this too, but it doesn't matter. One gate maps to the other, but this is not important because they all commute. So they are all in a same commuting layer, so there's no really intrinsic order in applying them. So it doesn't change the circuit. And then again, with the other one, this is better because it's also like on our gate set. So the Toffoli gates, they are examples of threshold gates. And here we have these qubits here, that's the symmetry X. Yeah, those are called the active qubits. And then we have the symmetry group that acts on them. And then if you permute this by symmetries, then it won't change the circuits. It will just up to commuting reordering. So like this gates and this gates get swapped, but they commute, it doesn't matter. So this is the gamma. So these active qubits, they encode kind of the inputs. So they are really the structure that you're considering, that you're trying to compute over. And then a quantum circuit said to be gamma symmetric if every symmetry gamma in these active qubits can be extended to an automorphism of the circuit. So there will be another permutation of the workspace qubits that if you compose those two, it will give an automorphism of the circuit. That's the formal definition. But the important thing is the intuition that I said before. And yeah, so this is in a sense a minimal quantum extension of the notion of symmetric threshold circuits that has been studied before in the classical setting. So like if we don't say all single qubit gates, but just X gates, which means not in the classical setting, and then all these threshold gates, then you will get like a quantum way of writing the notion of symmetric classical circuits, symmetric threshold circuits. So in a sense, you are just taking that definition and putting single qubit gates and seeing where it goes. And these threshold gates might not appear natural to everyone, but they are quite natural in the sense that they are robust. If you will say, oh, what about parity? Then I say, okay, put a parity gate thing. I don't care because it doesn't change the class actually, because you can compute it. So actually adding any permutation symmetric gates to the gate set does not change the class. So there's a very strong robustness to it. Okay, so now I defined this. So what are they good for? So in the classical setting, they study this a lot, and they have a lot of interesting algorithms that they can do symmetrically. So for instance, solving linear programs and STPs. And well, finding the size of a maximum matching here, and also deciding all minor closed graph properties. There's nothing quantum about this, though, but like since the quantum is a superset of the classical, then those can also be done quantumly. But what about real quantum stuff? Well, there are some very important quantum subroutines that can be performed symmetrically for any symmetry group gamma. So here, like amplitude amplification. If you recall the amplitude amplification, you have an algorithm A that prepares like a superposition of a good state and a bad state. And then you have an algorithm that distinguishes the good state from the bad state, and you want to create only the good state. And then you can do this efficient, like in the usual way, but you can also do it efficiently symmetrically, in the sense that if both the algorithm A and the distinguisher algorithm are gamma symmetric, then you can compute the good state symmetrically. You can prepare it symmetrically. You can also do like this oblivious and everything, but yeah. And also like phase estimation, if you have a symmetric unitary, then you can compute the phase of any given eigenvector, eigenstate symmetrically. And linear combination of unitaries, if you have a bunch of unitaries that are symmetric, then you can do a linear combination of them, well, with the usual caveats that is symmetric as in a symmetric circuit as well. And now what about real algorithms? For this, I want to focus more on this permutation symmetry, so like the full permutation symmetry group, which is the simplest, and in some sense, well, in many cases, it's the most important. So like in quantum information theory, we have this notion of symmetric subspace, which is very important. It's essentially like the simplest, but still, I would say the most important part of Schur-Hegel duality is given by the symmetric subspace, which is the space of all n-qubit states that are invariants under qubit permutations. So for instance, the uniform superposition over like all computational basis states that have a fixed Hamming weight. This is a symmetric state. It belongs to the symmetric subspace. And this thing, it has a lot of applications in quantum information theory. So for instance, optimal state estimation, cloning, and also the definite theorem. So what we can prove about this is like symmetric state preparation. So every symmetric state can be prepared by an SN symmetric quantum circuit of, well, supercubic size. So let's say efficient. But the interesting thing here is that, of course, you start from the all zero states, which is, of course, permutation symmetric. If you apply a symmetric quantum circuit, you can only get states on the symmetric subspace. And then what I'm saying here is that you can efficiently get all of those. So there is kind of an equivalence between what's possible information theoretically and what's possible computational efficiently, which I think is very interesting. There's no clear analog in in the unrestricted setting of such results. And it's not only about preparing states, but if you are given any unitary that's like maps the symmetric subspace to itself, then you can efficiently implement the restriction of this unitary to the symmetric subspace by a symmetric circuit. So it's something that can be done. And like going also beyond the symmetric subspace, something that I find very interesting is that like this permutation equivariant quantum neural networks that was proposed by Schatz et al., they can be, well, efficiently, but also naturally expressed as a symmetric quantum circuit. And the more important thing here, more than efficiently, is the naturally, because it actually shows that like there is this geometric quantum machine learning, this kind of fields that uses the symmetries in order to make better quantum machine learning models. And then they have this notion of symmetries that's very important to them, that they want to make the circuits that respect those symmetries. And I'm saying that they are pretty much essentially the same thing that we are trying to do here. So it kind of has an extra motivation from a practical perspective, not only a theoretical perspective, that you want to do better quantum machine learning models. So it's, yes.
Where does this 0.75 come from?
I think it's 11/4 or something. But the thing is that
It's not 3/4, it's.
yeah, no. I mean, it's just 3/4. But I mean, okay, the thing is, you prepare jig states first, and then like this has, okay, you can prepare it. I think you use the amplitude amplification, but this would give like a root. But where's the other one? Yeah, to be honest, I don't quite remember right now, but it comes kind of naturally if you try to apply. Essentially, the proof of both these theorems is applying all these three, or actually only the first and third, to specific circuits, and then this is what you get in the end. I would have to check to tell you exactly.
87.5 is not exactly, it's like some other thing.
No, it's 3/4 is 0.75, and then there's a 2 extra. Yes.
Does your statement mean that does it only imply that there exists a circuit that makes a state, or does it mean that given a description of a
Yes.
state, you can actually make it as well?
Yes. Yeah,
So
we
because
can
for every-
also.
For every state, you can consider just like the uniform superposition over all different permutations, which is, I guess, symmetric, right?
Yeah, and the uniform superposition of all permutations of a state is, yeah, it's there.
For every state, you can implement that state.
Yes. Yeah, there is this like jig states preparation. That's even Martin has a paper on this as well. This is important actually in some variation of quantum algorithms to prepare these symmetric states. And so it has been studied before. I'm not sure if there is a result in the literature saying that you can efficiently prepare all symmetric states. I don't know if people care about this, but like this is a result saying this, but essentially if you can prepare this jig states, which they know how to do, then you can also do this essentially by kind of a linear combination of unitaries, because you do a linear combination of the circuits that prepare jig states, and the jig states, they form a basis of the symmetric subspace, and that's how you. So we use this. We first we prepare the jig states, and then we use that together with linear combination of unitaries to prepare all of the others. Yeah, this might seem impressive in some sense, but like to be honest, like the symmetric subspace is pretty small. It's like it has dimension n+1, so it's like linear in
That's
n.
surprising, yeah.
Yeah, so I mean, it's not that surprising exactly, but it is like, well, in this situation of SN symmetry, it's all that you can do. So in a sense, it's all.
Paper yesterday, they give preparation circuits for data states for arbitrary weights.
No, oh really? Yeah. I mean, yeah,
that
we can
helps.
put that. Yeah, I didn't see it.
And it was, that's all I know.
Okay.
I read the abstract and that's what it said.
Model, this paper 2 years ago, they showed even under the normal quantum machine model considered by sales law, you can, in some cases, you should still have some exponential speedup compared to the classical probability.
Oh, really? Oh, that's cool.
It's by Casper. Yeah, I can say you.
Yes, yes, please. Yeah. Oh, yes. And now what we are all here for, what everybody wants to do. We want to prove a quantum advantage. And I did it. Just, but okay, so we consider this problem XOR sat. What's that? You have a bunch of clauses that are given by literals and negation of literals, and then you take the XOR, so the exclusive OR, instead of the usual OR for the sat. And then, well, you can do it like this if you want to say that, it looks like very hard to solve. Or you can put it like this to say, oh, it's actually easy. It's like you are given essentially a matrix, a Boolean matrix, and you are given a Boolean vector. And you are asking, is there a solution to the system of equations over? Yeah, it's the same thing because addition and mod 2 and parity are the same. XOR are the same. And then we can solve this problem efficiently using Gaussian elimination. Okay, now this problem, what's the symmetry of it? Well, this problem is symmetric with respect to rows and columns permutations. So like by just permuting the rows of the matrix and of the vector here, or by permuting the columns of the matrix, it wouldn't change the solvability of the system. It would just change the name of the variables. So this is the symmetry. And now, why do I say there's a quantum advantage? If we can do Gaussian elimination, well, turns out we can't. Gaussian elimination cannot be performed symmetrically without an exponential flow. And this is kind of, this is very interesting. Like it's intuitively, it makes sense intuitively if you think that for Gaussian elimination, you have to get these pivots rows and then like perform operations on all others with this pivot. And then you have to do this like for every row. And then like there's no way of choosing this pivot thing symmetrically in a permutation symmetric way. And then actually this was proven formally by Atsarias, Bulatov and Davar, that actually you cannot have any algorithm that computes XOR that solves XOR sats in a symmetric way. Yes.
Is this then deterministic, or does it also include probabilistic?
This is deterministic. Yes. And then like so they proved that there is an exponential lower bound for solving these XOR sats in the deterministic, which is the way they use symmetric computation. And then we proved that we can efficiently perform Gaussian elimination in a symmetric way using symmetric quantum circuits. And so this gives an exponential quantum advantage over in the symmetric setting. So over this analogous defines like classical and quantum classes. And this is one of the few computational models where we can prove such quantum advantage. So together with, as I said before, the query model and the shallow circuits. Okay, and now those are the results that I wanted to say. Yes.
How do you do this? What's the trick?
You're not gonna tell us how to do this.
What's the quantum trick here?
Actually, the quantum trick is to prepare these sticky states of superposition of one element. And then like on that element, that's like the pivots.
Yes.
Yeah.
To follow up on my earlier question, can't you do this classically by just flipping a pivot coin?
Well, you have to, you have to define it in the randomized way. I don't think anyone defines this randomized model of symmetric computation. So depending on how you define, then you can probably do, or you can probably not.
Okay, but this might be a sort of a classical speedup, so not you're just using the randomness of this.
Exactly, it might be. This is unclear, but it's like it's kind of how to say ongoing work.
Okay,
you
can write another paper where you
exactly. It might be that this is just random, but like I do believe that there is a real inherently quantum speed up, just not maybe for this problem.
Okay, fair enough.
Yes.
In the quantum version of the problem, how is the input specified?
Oh no, yes,
like
it's
a product state with the coefficients.
Exactly. It's like a computational basis states, like you put the entries of the matrix as zeros and ones in the computational basis. So it's the usual classical way. The exponential here is just because of these incredible results that you cannot do it symmetrically in the classical setting. because
Most of the work is done in the lower bound.
exactly.
Yeah.
But it is actually an interesting quantum
Yeah,
circuit,
cool.
like the
Okay.
way that you use the decay states to choose the pivot, because it's not quite clear how to do that.
But sorry, can you just like measure this decay state before you start reversing the algorithm?
I mean, you can, we show also that's like in this, you can allow for intermediate measurements and it doesn't change the class. So
Yeah, no, but like basically, I'm just wondering, is there any like interference effect going on? In the
no.
algorithm?
So
But
in the
then
sense, it is a random
Yeah,
thing.
but then it seems like you should just define, like, yeah, I guess then the analog classical algorithm would be that you just need to be able to sort of sample from this kind of decay state distribution, like basically.
Yes, if you
prepare
can
decay state
sample
and
that.
measure, you can sample from that.
Yeah, exactly. If you can sample from that, then you can do this. Yes. And then you have to define a model where you can do that. This hasn't been done, as far as I know, so. Yeah. But yes, I am claiming a quantum advantage over the deterministic one, not the randomized one, which doesn't exist, to be fair, so, so it's okay. Okay, and then to finish, I want to, let's say, about future direction. So there are a bunch of open questions that I find very interesting, and so I'm going to say a bit about them. So yeah, I mean, one of them is actually to find a real quantum advantage that's not just like a randomized advantage, but I didn't put that one, but it's another one. Okay, so the first is methods for obtaining lower bounds for symmetric quantum computation. So we have those like very good methods for obtaining those in the symmetric setting. And now the quantum setting, we just like put some single qubit gates. And so, I mean, come on, how hard can it be? It's like, okay, but maybe it might be very hard actually, but like the way that I like to put this question is like, well, there are two ways of framing it. Which quantum algorithms require symmetry breaking for efficient implementation? So like we saw that Gaussian elimination, this one. And which ones do that even in the quantum setting? I don't know. And more interesting, which problems cannot be solved efficiently at all? Of course, this is something outside of the model. So we can just kind of, after we get an exponential or whatever lower bound, then you can think, oh, is there any reason to believe that breaking the symmetry here would help or not? And then like this would give an indication that the problem is hard, but not a formal proof, but still it's interesting. And then when a symmetric quantum circuit is classically simulable, so as has been pointed out, for restricted and not symmetries, by which I mean full permutation symmetry, this can be done. This was done by Anshul et al. So which other kinds of symmetry allow for algorithms that classical algorithms are simulated? And then can the symmetry constraints of the symmetric quantum circuits be leveraged for error mitigation? Because like error mitigation is very much symmetry based. Like it's always been a very important part to consider the symmetries of the states. And here we have quite a lot of symmetries built into our circuit. So like, can they be leveraged in some sense? And then another, can symmetric quantum circuits efficiently deal? Oh yeah, this is an interesting question that was suggested to me by Karajan, which is actually in the classical setting that I said that we kind of build upon that. They only consider relational problem, like relational structure symmetry. So essentially graphs. They deal mostly with graphs. Those are very interesting in the classical model, but in the quantum model, we have very different kinds of symmetries that we can do. And it's like, this is something that would go significantly beyond what's done classically. So I think it's interesting. And finally, something more open-ended, but I find extremely interesting is that there is a model of symmetric computation that was given by Irma Martin, where the symmetry is SU2 symmetry, so it's on the qubits. And then, so it's more maybe physically motivated. And like, it seems to me that there should be some kind of Schur-Weyl duality that maps those two in some way. And this, I believe this is true, not just because, well, SU2 and SN are kind of Schur-Weyl duality, but like there are some results that are very analogous in both settings. And I think that making this connection precise, if we can find a formal relationship between these two models, that would be very interesting. Yeah, those are the questions I had. Well, thank you.